Okay, last class we took some discussions on structural geology, in which subject we could know and learn how to recognize the imprint, the natural imprint that Earth left in history. So today we are going to focus on the larger scale movement of Earth's plate, the continental drift and plate tectonics. So the contents of this chapter, we will learn how our continents are located at current position, from which we could understand the earthquake better in our later chapters. Okay. So plate tectonics is a scientific theory that extends 2 centuries of often puzzling observations and hypotheses about our planet Earth. I'm sure all of you have seen this cartoon of the theory, which suggests the continents drift slowly across the face of our planet. And it is noted that the continental drift is a concept with a long history. So yeah, it's a theory about the observation of the match of characteristic geological provinces between the continentals. Actually, in the 17th century, the famous philosopher Francis Bacon has already commented on the similar form of the western coast of Africa continent and the east coast of the South American continent. That is Atlantic coast of Africa and the Pacific coast of South America. And also some other observers, and he have noticed that the similarity or fate of the Atlantic coastlines of South America and Africa, and even with having suggested that they were once together and had drifted apart. And a century ago, geologists puzzled over the fate of shorelines of Africa and South America and proposed some more mature sceneries. And they noted that the fossils of extinct net-bound plants and animals, glacial deposits, and ocean lava flows could be meshed together along coastlines that today are thousands or kilometers apart. So yeah, it's really amazing phenomenon. And also the core forms in, as we know, the core forms in tropic climates, and but the core was found in Antarctica, which where is very cold currently. So this implies that the Antarctica have moved in the past. Yeah, it's easy to understand. And faced with this positive data, the scientists developed hypotheses to explain them. So the most famous one is the Alfred Wegener. He proposed the most comprehensive early hypothesis for continental drift in 1912. So for the first time, it was considered that drift is taking place in history and has taken place at least throughout the past 200 million years of Earth's history. So this guy, Alfred, devoted much of his life to its development. So he detailed much of the older pre-drift geological data and maintains that the continuity of the older structures, formations, and fossil and floras across present continental shorelines was more readily understood on a pre-drift reconstruction. And he also proposed that the mineral specimens along the supposed break lines of the continents are nearly identical. And some identical species exist on certain continents, like earthworm common to both Africa and South America, suggesting the species could not have spontaneously arisen on both continents without some variations. And indications of widespread glaciation from about 380 to 250 million years ago are evident in Antarctic, southern South America, southern Africa, India, and Australia. And if these continents were once united around the south polar region, this glaciation would become explicable as a unified sequence of events in time and space. So, the Wegener truly pushed the continental drift scenery forward at the moment. And his theory of continental drift could explain a number of problems that existed during his time. And first of all, his theory has explained the feat of the coastlines along both sides of the Atlantic, including Eastern Africa and Western South America. And secondly, it explained the linear and narrow shape of the mountain ranges, and then the dominance of two levels of global altitude, the deep sea abyssal plains and the broad continental lowlands, has been accounted for. And at last, the otherwise inexplicable appearance and in its appearance of land bridges that were necessary to explain the final exchange between continents now separated by large oceanic areas. And this map shows the distribution of Plasmatocolea vermicularis, species of leafy liverwort. And this plant is known to have a limited capacity of dispersal. And it would be next to impossible for it to cross the Atlantic Ocean in order to populate the two continents. And it presents distribution most likely the result of scattering of the species at the south coast of Gondwana before spilled into the present continents. And the scientist Alfred Wegener, he published his works that attempted to add a credibility to his theory of continental drift. And although his observations were supported by geographic feet, fossil evidence, and geologic patterns across the Atlantic, he was never able to convince a skeptical audience who demanded more proof. So that means his theory was widely rejected during his time because the reasons below. Yeah, the first one is that the ocean floor was too strong to be pulled aside, and which he has not explained. And secondly, the Wegener had not proposed a plausible force that could induce the continents to drift. And uh, any attempts to test his hypothesis with observations had mixed success. So, namely, he needed a more detailed explanation for the mechanism that propelled the continent's long distances to support his scenery. And yeah, it's pity that after Wegener's death, after he died, the continental drift scenery quickly fell out of scientific attention. And nobody cares. Very few people cared about his scenery because he had aroused great scientific hostility in USA, especially in USA. But meanwhile, in Europe, a few scientists continued to examine some of his ideas that for the ideas that would lead eventually to the scenery of plate tectonics. So 50 years later, after the theory proposed by Wegener, the theory of plate tectonics was born in 1960. And while many of the geologists mentioned above were looking at the rocks exposed at the surface of the Earth, and several alpine geologists began to look deep into the Earth for answers regarding the origin of mountains. And the general acceptance of continental drift was achieved in the 1960s with the development of the plate tectonic sceneries. And model investigations of the previous inaccessible ocean floor, and particularly the discovery of the striped pattern of magnetic polarities at both sides of the mid-ocean ridge led to the concept of seafloor spreading, which is the dispersion of ocean floor from the mid-ocean ridges. Later, I will explain what the mid-ocean ridge mean. And the plate tectonics theory dealing with the dynamics of Earth's outer provides a uniform context for understanding mountain building processes, volcanoes, and earthquakes, as well as the evolution of Earth's surface and reconstructing its past continents and oceans. So, plate tectonics is the process by which Earth's hot interior loses heat, and we can measure the slow drift of plates worldwide using satellite navigation systems like GPS, which is the best way for the current technology. And the basic premises of plate scenery are secure because they can be tested against a wide variety of observations. And according to the scenery, the outermost two layers of planet Earth, the mesosphere and the asthenosphere, are directly involved in plate tectonics. The mesosphere is a rigid outer layer, which is typically about 100 to 3,000 kilometers thick and overlies a plastic layer called the asthenosphere. And the mesosphere and the asthenosphere are the only parts of the Earth described in detail here in this plate tectonics scenery. But the size of individual plates is significantly different. The layer of lithosphere ranges in thickness from about approximately 70 to 150 kilometers or more. They are thicker below the continents and thinner below the oceans. And beneath some mountain ranges, it may exceeding 200 kilometers in thickness. It consists of two components: the oceanic crust and the continental crust. The two components include the crust and the lithospheric part of the mantle. And the lithospheric metal behaves in brittle fashion and contrasts in this regard from the underlying plastic-like asthenosphere. And the asthenosphere behaves in ductile fashion and locally contains pockets of molten rock. And this above point out the significant difference between the continental drift and the scenery of plate tectonics. Notice that the continental drift suggested that the continental blocks somehow plowed through the oceans, but the later plate tectonic scenery pointed out that the rigid plates containing both continental and oceanic crust moved on the top of ductile metal. So you see the difference? Yeah, the earlier continental drift just pointed out that the continental blocks just plow away apart and through the oceans, but it had not explained how they separated apart. But the plate tectonics scenery, it explained the rigid. Although the plates are rigid, but they can move on the top of the ductile metal, which has a very high temperature. And the lithosphere is broken up into 7 very large continental and ocean-sized plates, 6 or 7 medium-sized regional plates, and several small ones. And these plates moved relatively to each other, and typically at a rate of 5 to 10 centimeters per year, and interact along their boundaries, and where they converge, diverge, or slip past one another in such boundaries. And such interactions are thought to be responsible for most of Earth's seismic and volcanic activity. Seismic means earthquake. Yeah, although earthquakes and volcanoes can occur in plate interiors, and the plate motions cause mountains to rise where plates push together or converge, and continents or to fracture, and ocean to form where plates pull apart or diverge. And the continents are embedded in the plates and drift passively with them, and which occurred over millions of years, results in significant change in Earth's geography. And as to the topography between the ocean crust and the continental crust, there's an ocean trench, and which occurs where oceanic lithosphere and the continental lithosphere converge at the boundary between the two plates. Because the oceanic lithosphere is the denser of the two, which means the oceanic lithosphere, the dense of the oceanic lithosphere is larger than the dense of the continental lithosphere, and it descends on the active continental margin and sinks into the deeper mantle. And the larger flat abyssal floors of the open ocean lie 3 to 6 kilometers before the sea level. And the the crust of Earth, which forms the uppermost 5 to 6% of the plate, is generally divided into two types, continental and oceanic crust. And the continental crust has an average thickness of 30 to 40 kilometers, but range up to 70 kilometers on the mountain ranges and the high plateau like the Andes or the Tibeto plateau, which I have talked many times. And the oceanic crust is remarkably thinner, with a typical thickness of 5 to 8 kilometers, and forms the ocean floor. And the top of oceanic crust lies average 4 to 5 kilometers deeper than that of the continental crust. And the rocks beneath our feet are exactly solid, but they are not rigid. Can you understand this? Yeah. So what Earth's surface features can tell us? Now here I will explain some terms like topography is referred to the relief and the form of the land above the sea level. That means the geomorphologic characteristics and the geometry features of the land above sea level. And the bathymetry is referred to the topography on the ocean floor. And the Earth bulges around its equator and is slightly flattened at the poles of the Earth. And all the evidence points to the centrifugal force caused by Earth's rotational spring. And this support give us a proof that what kind of force pushed away the continents during the continental drift. And the distribution, the elevation distribution of the height of the Earth's topography, and the depth of the ocean portion is like a bimodal. There are two peaks for this diagram, and the continents average about 4.5 kilometer elevation above the sea ocean floor, and they stand notably higher than the ocean basins because the thick continental crust is relatively light, and the thin oceanic crust is relatively heavy, which has average density 3.0 gram per cubic centimeters. And this lithosphere floats on the asthenosphere, which is a ductile portion. And the bimodal elevation of the Earth is a direct reflection of the difference in composition and density between the continental and the oceanic crust. Yeah, as I mentioned, they have different densities. And the continental crust
consists of relative light material that composed of acidic or granite rock, like granitic and metamorphic rocks. For example, granites, some gneisses and schist. So the expression that the continental crust is granitic. And as in comparison, the thinner oceanic crust is relatively heavy, and it consists of basaltic rocks, mostly including mostly basalts and gabers, and the density, is a little bit larger than the continental crust. And the calcium-rich feldspar and pyroxene are the most important minerals in the ocean crust. And these different mineral materials results in the different density of the oceanic crust and the continental crust. And why is Earth's topography? Why does it seem like two peaks, like bimodal? And firstly, the principle of isostasy governs the rise or subsidence of the crust until mass is buoyantly balanced. That means buoyancy develops that needs to increase in topographic elevation. And secondly, according to isostasy, all parts of the lithosphere are in a floating equilibrium. And low density wood blocks float high and have deep roots, whereas the high density blocks float low and have shallow roots. And all above finally resulted in the bimodal shape, topographic shape of the Earth. And this figure shows the land versus water on the Earth's surface. And we can see the ocean covers exactly 71% of Earth's surface, and the land occupies only 29%. And in particularly, the land area occupies 46% in the northern hemisphere, and while the water area occupies 53%. But for the southern hemisphere, the land area occupies only 12%, and the water area could occupy 88%. And the sea level fluctuates over time when the climate is colder and water is stored as ice, and which will lead to the resulting that the sea levels will fall and the shoreline would move seaward. And in comparison, when the climate gets warmer, the ice would melt and the sea level would rise, and the shoreline advances inland. And the plate motion results in three types of plate boundaries: the constructive, destructive, and conservative. Constructive plate boundaries are characterized by divergent plates, and it commonly referred to as divergent divergent plate boundaries. And the developing gap along the line of separations is immediately filled by a newly formed lithospheric material, including ocean crust. So it is termed as a constructive plate boundary. And the constructive plate boundaries are presented by the mid-ocean or ridge, which is undersea mountain range, and that circle the Mars like seams on a baseball. And the ridges are formed by rising basaltic melts generated from the metal asthenosphere below them, and that solidify to a brittle ocean crust. And the topographic mid-ocean ridge reflects the warm, less dense lithosphere that underlies it. And the ocean's floor spreads from constructive plate boundaries, so it is also called seafloor spreading. And the second type is destructive plate boundaries. It is characterized by converging plates, and where two plates move towards each other, the denser plate is bent and pulled beneath the less plate. It means this portion has a greater density than this portion, and eventually plunging downward at an angle into the depths of the sublithospheric mantle. And such areas are called subduction zones. Eventually, the subducted plates become recycled into the metal and thus destroyed. And the third type is the conservative plate. And the conservative plate boundaries occur where the two planes slip past each other, and little or no crust is created in such a process. And these boundaries are also characterized by a strike slip. You remember strike slip fault? It's very similar to this such a process, and they are characterized by strike slip or transform faults, and are commonly called transform margins. And this map shows the distribution of the plate boundaries for the different types, and we can see the mid ridges on the other hand are cut by numerous, mostly relatively short transform faults, and the prolongation of oceanic transform faults contain fracture zones with little tectonic activity that in many cases can be traced for long distance on the ocean floor. And where the oceanic transform faults intersect continental crust at oblique angles, the fault can penetrate deeply into the adjacent plate and create distance of lateral offset, and the San Andreas Fault of California is such a good example that which have already showed the photos last week. The early fault have been offsetted by the later fault. And indeed, the motions of the individual plates can be described by their relative movements along the plate boundaries. And as a geometric constraint, the sum of the moments of all of the plates must result in zero. And from a global perspective, the drifting apart of the plates at constructive boundaries must be compensated by the opposite movement and the destruction of lithosphere at destructive boundaries. And speaking of the topographic of the seafloor, the continental shelf steepens slightly at 100 to 200 meters below the sea level, and the continental slope is the flooded continental margin, and the continental rise descends more gently from the base of the continental slope. And meanwhile, the German research discovered the large, non-stretched submarine mountain ranges that today are known as mid-ocean or mid-oceanic ridges, and are key. It is a key to the concept of modal plate tectonics scenery. The mid-ocean ridges are referred to the constructive plate boundaries, as I mentioned in the last previous slides. And the earthquakes and the volcanoes are common along such active margins. And looking at the distribution map of earthquake epicenters, which is black points on this map, which marks as the points at the Earth's surface directly above the earthquake center. It's called epicenters, and it impressively shows that earthquakes are mainly restricted to narrow zones around the world, and which is the present plate boundaries. And the distribution of earthquakes varies at different types of plate boundaries. The deep earthquake centers occur only along the subduction zones, whereas shallow earthquakes occur at all types of plate boundaries. And moreover, the distributed earthquake centers can be found elsewhere, as some elsewhere, indicating that the plates are not free of deformation in their interior parts that may be cut by large fault zones. And underneath mid-ocean ridges from continuous feature more than 60,000 kilometers long. And the mid-ocean ridges and the mid-ocean ridges marked where the two oceanic plates spread apart, and the rates of movement at the plate fault zones are generally less than a few millimeters per year when averaged over long geologic periods of time. And this tends to be an order of magnitude less than rates at plate boundaries. While new parts of plates are created along the mid-ocean ridges, the old parts of plates disappear in subduction zones. And on the other hand, the passive margins have very few earthquakes and little volcanic activity. This figure also presents the global distribution of earthquake centers with epicenters mapped according to their depths. And globally, earthquakes are strongly concentrated along the destructive plate boundaries, you see, and are especially notable really in the Pacific Ocean. And zones of epicenters are relatively wide because the subducting plates that produce earthquakes plunging obliquely into the metal. And subduction zones can be traced downward using earthquake force, which means location and the depths of the earthquakes to depths of about 700 kilometers. And the map view of the plate boundary is located at the trench side of the earthquake belt, where the centers are at shallow depths, and the boundary plunges downward at different angles. And the earthquake activity is much less. Actually, it's earthquake is much less at the middle ocean ridge. The uprising currents transport molten rock material to the Earth's surface, and the stiff shell that accumulates and release stresses is quite thin. And hot and recently solidified rock material is more likely to deform plastically. And therefore, only small, shallow earthquakes occur, but only small shallow earthquakes occurred in the mid-ocean ridge, not like the fire ring surrounding the Pacific Ocean. But the constructive plate boundaries are also clearly visible on the earthquake map. Next, let's move to Earth's internal phenomena. And it is not difficult to know that the rocks are poor conductors of heat, right? And so the Earth moves its internal heat by moving the rock itself. And the circulation of hot rock is maintained by metal convection. And the Arthur Holmes, a geologist, proposed that convection currents were the driver of the Earth's tectonic system. And the convectional currents in the subnesospheric metal are interrelated to overlying plate motions. And based on the propagation of behavior of earthquake waves, it is known that the Earth's metal is primarily in a solid state. And however, it is able to flow on orders of 7 centimeters per year. And this value is close to the velocity of plate motion. So to sum up, convection is the process by which heat moves through the solid rock, and it can happen in gas, in liquids, or given enough time in ductile solids. And it is also a prerequisite condition for metal convection is thermal expansion of hot rock. And as we know, rock would expand when its temperature increases, and its density thereby would decrease slightly. And the hot rock is buoyant relative to a cooler rock in its immediate neighborhood. And once a percent expansion requires an increase of about 400 degrees and leads to a 1% decrease in density. And the viscosity is the propensity of rock to ductile flow. As far as we know, rock is solid, and it does not need to melt before it can flow. So the presence of water encourages flow in solid rock. And the convection currents bring hot rocks upward from Earth's interior. But the rock in the lithosphere is too cool for convection to continue under such a context. So the heat moves through the lithosphere primarily by convection. And the lithosphere to asthenosphere boundary is about 1300 degree, and depending on the Earth, on depths. So it can provide the enough heat and temperature to make the rock ductile, which can facilitate the crust drift. And below the lithosphere, rock masses in the deeper metal rise and fall according to differences in temperature and buoyancy. And the densest lithosphere is most likely to sink back into the asthenosphere and the deeper metal. And the ocean floor and the continents are slowly moving, which has a maximum velocity of 12 centimeters per year. And the relative movements of the plates along the plate boundaries induce earthquakes, as I introduced. And the gliding process between the plates produces great but variable stress. The stress is induced along the steep planes within rocks, and which to a certain degree are elastically deformable, and is released in a jerky movement when a limiting value is reached. And on continents, the hotspots are commonly related to graben structures characterized by extensive deep fault systems that cut through the entire thickness of continents. And when continents split apart, a new ocean basin could form. The best known example are the volcanoes of the East Africa graben system and the Red Sea that was formed in this way 30 million years ago. And the graben structures are characterized by crustal extension and bordered by faults. Such areas cause thinning of the lithosphere and provide the opportunity for magma to rise along the fault zones. And if extension continues, the new ocean can be formed at these structures like this Red Sea. And it is attributed to subduction, and which is a process that old lithosphere sinks beneath the edge of an adjacent plate. And as to the geothermal gradients, the temperature will greatly increase with increasing depths from lithosphere to asthenosphere. And the temperatures rises in subduction zones at 5 to 10 degree per kilometer, and compared to a normal geothermal gradients in continental crust of 30 degree per kilometer. And such a gradient is a progressive change in some physical or chemical property. And such as geothermal gradient varies widely with geography from 5 degrees to 75 degrees per kilometer. And the oceanic lithosphere is about 100 kilometers thick, and the geothermal gradients in oceanic lithosphere is 300 degree per 100 kilometer, and the average continental lithosphere is 200 kilometer, and the average geothermal gradient in continental lithosphere is about 67 degree per kilometer. And next, I will talk about the techniques which could be used to measure the plate movement directly. And since 1970s, several attempts have been made to measure plate movement directly using satellite laser data, which is short for SLR technology, and very long baseline interferometry, which is short for VLBI. And these techniques have been replaced during the recent 20 years by measurements with the global positioning system, GPS. In the 1960s, the U.S. Department of Defense established this network of satellites with orbits that could be used for reference in precisely determined location. And the GPS could detect very small movements of the Earth's surface. Yeah, it is the best way so far to measure the movement. And it is accurate within 1 millimeters. And 2 measurement methods are included, which are as below. The first, one of the measurements is the GPS campaign. The researchers established a network of fixed reference points on Earth's surface and often attached onto bedrock. The position is remeasured every few months or years. And the other one is continuous GPS measurement. The receivers are attached permanently to moments, and the position is estimated at fixed intervals of a few seconds or minutes. This map shows the changing distances as determined by GPS measurements. The reference points The reference points are the Koki Bay at Hawaii and the Witzel in the Bavaria forest in Germany. And the data, which is showed as red numbers in the unit of millimeter per year, covers the time span from January of 1993 to the May of 1995. And the values calculated using the model are given for comparison. The model of Newville model are given for comparison, which is shown as blue numbers in brackets. And the values, is shown on the line or below the line. And we can see the GPS data indicate that the mid Atlantic ridge moves very slowly eastward, since the eastward direction component of the African plate is larger than the westward directed one of the South American plate. And about the types of plate margins. At first, I need to address that the lithosphere currently consists of 12 large plates, including the 7 largest plates, containing the North American plate, South American plate, Africa plate, Pacific plate, Eurasian plate, and Australia, Indian plate, and the Antarctic plate. And about the classification, the plates have 4 kinds of boundaries or margins. The first type is divergent margin, and it is also called spreading center. And the forming process is that the magma rises to form new oceanic crust between the 2 pieces of the original plate. And the second type of convergent plate boundary represents the active continental margins where oceanic lithosphere is subducted beneath the continental lithosphere without a marine basin behind the volcanic arc. And there are that the arc is built directly on the adjacent continent. And the continental margin is connected directly to the hinterland. And although shallow marine basins may exist behind the volcanic arc. And the third type of convergent margin is a zone of is called collision zones. And if 2 continental masses collide during continuous subduction, they eventually merge, and the telescoping of the 2 plates and the buoyancy of the subducting continent eventually needs to stand still of subduction within the collision zone. And the 2 colliding continental plates create a mountain ridge during such a convergent margin. And the fourth type is transform fault margin, and which forming process is that the 2 plates slide past each other, and the grinding and abrading their edges. And this is the distribution of the 4 kinds margins. And yeah, you can see here it's the Himalaya mountains. I have introduced that to the Himalaya mountain was produced by the collision of Euro-Asian plate and the Indian plate. And here it belongs to the Australia-Indian plate. And finally, the convergence margin. At convergence margin, the Himalaya mountain, which is named as the world's proof, has been formed. The next time I will show you a video to present the world's greatest geological wonder, the world's proof, the uplift of the Himalaya mountain, and how the Tibet Plateau was formed.
Hello, my name is Michael Wysession, and welcome to Lecture 8 of our course on the geologic wonders of the world. Now, in the last lecture, we looked at the Grand Canyon in Arizona. In this lecture, we're going to go around the world to visit a place with lots of big canyons and lots of big mountains and frankly, lots of big everything. The Tibetan Plateau, including the Himalayan mountains. When viewed from space, it is likely that there is no more impressive geologic wonder than the Tibetan Plateau. It's 2.5 million square kilometers of land that's approximately 5 kilometers above sea level. It's called the roof of the world. The Tibetan Plateau contains the world's highest mountain range, the Himalayas, sometimes also called the Himalayas. It contains the world's highest mountain, Mount Everest, at over 29,000 feet. It contains a lot of high things. Now, there's actually a lot of different ways to define high or tall or big. As a mountain range, and again, with a mountain range, we're talking about a long chain of mountains that usually form at the collision between two tectonic plates. As far as mountain ranges go, the Andes in South America are by far the longest, more than 7,000 kilometers. The Himalayas are only 2,400 kilometers in comparison. The Andes are currently growing by the subduction of the Nazca Plate, part of the Pacific, that we saw in Lecture 3 on the Galapagos Rift. That subduction occurs beneath the whole extent of the west coast of South America. It's the longest continuous subduction zone in the world, and therefore the longest mountain range. As far as a single mountain on land is concerned, Mount McKinley, or Denali, in Alaska, rises farther from the surrounding valley than any other mountain on land. It's 18,000 feet above the surrounding plains. For Mount Everest, it's only 12,000 to 15,000 feet. Not only is Denali the result of the collision between North America and the Pacific plates, with lots of thrust faults that have lifted up the rock, McKinley is made from a giant mass of hard granite, so it erodes more slowly than other mountains might. But McKinley is also forming from a compressional bend in the strike-slit Denali Fault, much like the San Gabriel Mountains north of Los Angeles, how they are pushed up by a bend along the San Andreas Fault. Only it happens on a much larger scale, and Denali is still going up. And as a single mountain, nothing compares to Mauna Kea on Hawaii, which rises more than 33,000 feet off of the seafloor. Now, most of this mountain is underwater, but if you take, again, the top of the mountain compared to the surrounding lands, Mauna Kea wins the prize. We'll see more of this in Lecture 24. And remember from the second lecture, the peak of Chimborazo in Ecuador, because it's at the equator, which bulges out compared to the rest of the planet, Chimborazo is the highest point measured from the center of the Earth. But it's impossible for anything to compare with the Tibetan Plateau in terms of just sheer size. For example, look at the number of tall mountains there. There are about 450 mountains in the world that are more than 7 kilometers above sea level. Every single one of them is part of the Tibetan Plateau. The next highest mountain outside of the Tibetan Plateau is Aconcagua in the Andes in South America at 6,962 meters high. The Tibetan Plateau doesn't contain a single mountain range, but many of them. Usually, if you go to a place like the Andes or the Appalachian Mountains, you have a long range, but it drops away on either side. It's not the case for the Tibetan Plateau. There is just mountain range after mountain range after mountain range. If you are actually there and view it, it is just an incredible sight. So many large mountain ranges exist in this part of the world. On the north side, you have the Kunlun Range, the Kilian Range in the northeast, which borders the Gobi Desert. On the east, you have the Hengduan Mountains in the Sichuan province of China. On the west side, you have the Karakoram Range in Pakistan. But most impressive of all, of course, is the Himalayan mountain range, which is at the southern end of the Tibetan Plateau and separates it from the Indian subcontinent. The Tibetan Plateau contains also an enormous amount of water, mostly in frozen form. The Himalayas alone have about 15,000 glaciers that carry as much as 12,000 cubic kilometers of ice down out of the mountains. In fact, the rivers that form from the runoff from these glaciers feed 3 billion people. I mean, almost half the people in the world get their water that starts up here in the Tibetan Plateau. You can see the major rivers that come off of here. The Indus River Valley coming down on the west side, the Ganges and Brahmaputra rivers coming out emptying through Bangladesh, the Mekong River that flows out through Southeast Asia, and then the Yangtze and Yellow rivers in China. Just an incredibly important source of water for a major part of the world. There's an interesting question there. Why is all this water here? Why does the Tibetan Plateau act as a source of so much of the world's water? Well, it's because it's a huge barrier to the monsoon air patterns. What happens in India? India has a monsoon type climate, which means for part of the year, massive, moist, warm airflow comes off of the Indian Ocean and heads north up across the Indian subcontinent. As it does, the rain falls and drops out. And then as it begins to hit the Himalayas, that air has nowhere to go but up. And actually a double layering of continental crust. You have the Chinese continental crust there sitting on top of the Indian continental crust. And that's part of the reason why the continental crust here is so much thicker than normal. Typically, if you look at a piece of the continent anywhere around the world, the average thickness is about 40 kilometers. In the case of the Tibetan Plateau, the thickness is about 80 kilometers. That's just how much rock has been smashed together. It also explains why you can go to the top of these mountains, top of Everest, and you find sedimentary rocks with fossils in them. This rock is limestone. It was once formed at the bottom of the ocean seafloor. The roof of the world is made of rocks that came from the bottom of the sea. Some parts are still rising very quickly. Nanga Parbat, for example, we know is now rising about a centimeter a year. Other parts of the Tibetan Plateau are eroding quickly. But here's an even stranger thing. Some parts of the plateau are actually rising faster than they are eroding because they are eroding. Now, this may sound totally paradoxical, but it makes sense when you look at the process of isostasy. Isostasy is the balance that affects the elevation of the continents. For instance, it's the reason why an ice cube pokes a little bit up above a glass of water. The ice is a little bit lighter than water, so the top of the ice cube sits above the top of the water. Well, the continental rock is a little bit lighter in terms of its density than the rock underneath. So when you smash continents together and you build up a big continental mountain, you also create a very deep root here. Well, as you start to erode the rock, then the whole continent starts to rise up. For instance, it's like sitting down on the edge of the bed. When you sit on the bed, the whole bed goes down. If you start to get up, the edge of the bed is going to rise up again. So as you remove away the top of the mountain, the whole plate starts to rise up. If you have a few peaks standing high, but you start carving away valleys, as you remove the valleys, the peaks will rise up higher. So it is possible to have your tallest mountains still going up, even while the rest of the mountain range is being eroded away. Now, you can go visit many of these regions, and you can do it the hard way or the easy way. The easy way, for example, is to fly into a city like Kathmandu, the capital of Nepal, and take a variety of tours and trips out from there up into the valleys. Kathmandu is a fascinating city with an ancient history. It's sacred both to Hinduism and Buddhism. But it sits in a very deep valley between mountain ranges, and it's not even a mile above sea level. I mean, it's lower in elevation than Denver, Colorado is. So the temperatures are mild year-round, and the air is easy to breathe. There's also a hard way. You can climb the mountains. These often involve long treks traveling from one base camp to the next, sometimes over many weeks. You need to be in really top physical shape to do this, not only because the height of the ascent and the incredibly low temperatures. Frostbite is very common for people who climb up in these mountains, but because of the thin air. By the time you get to an elevation of 5.5 kilometers above sea level, there's half as much air as there is at sea level. At the top of Everest, which is over 8.8 kilometers above sea level, the air pressure is so low, it's a third of air pressure at sea level. So a person who would normally have to breathe 20 or 30 times a minute would have to breathe 60 to 90 times a minute just to get the same amount of oxygen. Many climbers become physically exhausted simply from the act of breathing so heavily. As a result, people will often take bottled oxygen, and that's become the standard for use in climbing these tall peaks, ever since it was first used in 1922. So when Edmund Hillary and his guide Tenzing Norgay first climbed the summit of Mount Everest in 1953, they had bottles of oxygen with them. However, some of the top climbers today try the ascents without oxygen. In 1978, this was first done by Reinhold Messner, and he climbed Everest without any oxygen at all. 2 years later, in fact, he did it again by himself in just 3 days from the base camp at 21,000 feet. In fact, some climbers argue against the use of oxygen. They say it lets people up who might not be in top physical shape and have a greater risk of dying. I mean, frankly, a lot of people have died on Mount Everest. On one day in particular, in 1996, there were 34 people climbing Everest, and 8 of them died from the exposure. But as of 2008, Everest had been climbed about 4,100 times by 2,700 different people. The Sherpas there sometimes do it many times. There's one in particular, Apa Sherpa, who's climbed Mount Everest 21 times. And out of those 4,100 climbs, there have been 220 deaths. Because it's often impossible to get the bodies down, the path to Everest is actually lined with the frozen bodies of the people who didn't make it. It is, in any case, a great challenge to reach the mountains, and it's incredibly rewarding. In fact, the difficulty in reaching them actually caused it to take almost 50 years to even determine that Mount Everest was indeed the world's highest mountain. I mean, it's hard to imagine today with satellites and radar. We have laser altimetry, networks of GPS sensors. There's just an incredible technology that allows us to measure our land. Work back then was done by triangulation. You would essentially take known locations and you would measure the angles from 2 points to determine a third and keep working your way upland from the coast. This was first started back in 1808 by the British Great Trigonometrical Survey of India. And they came up with the height finally, almost half a century later, that Everest was the tallest. It wasn't until 1852, in fact. Andrew Waugh, who was in charge of the British survey, redid calculations that had been done over the previous decades, and announced that Everest was indeed the tallest mountain. That announcement didn't come out until 1856. The calculation that he made came out to exactly 29,000 feet. But they didn't want people to think they had rounded off the number, so they arbitrarily added 2 feet to the number and declared Everest as 29,002 feet tall. There have actually been many surveys made since then, both by surveying equipment and by satellite. And though the most common height given for Mount Everest is now 29,029 feet, there's actually still some uncertainty. The numbers vary from about 29,017 to 29,035 feet. So we still don't know exactly how tall Everest is. The Tibetan name for Everest is Jomolungma, which means Holy Mother. But Andrew Waugh named it after Colonel Sir George Everest, who was Waugh's predecessor as chief of the Indian Survey. Now, the Tibetan Plateau and the collision of India into Asia have two other very broad influences. The collision causes tectonic disruption throughout Asia. In fact, most earthquake-related deaths in the world are related to this particular plate collision. If you look at a map of this region, a tectonic map of Asia, you can see that there are faults all over the area. And the deadly Sumatra earthquake of 2004, that was related to this collision. It's the Indian plate colliding into Sumatra. 250,000 people died. In 2005, the deadly Pakistan earthquake happened at the west end of the Tibetan Plateau. That killed 75,000 people. In 2008, on the east end of the Tibetan Plateau, again on a fault that's a result of this collision, 70,000 people died. I mean, this is all India's fault. And the faults propagate throughout Asia, propagating inward, almost like if you took a shovel to snow and you kept shoveling and the snow just built up in front of your shovel. That's what's happened as the Tibetan Plateau has grown outward, and it continues to fault and rupture in the process. There's another very important factor, and that is the role that the Tibetan Plateau plays in cooling the planet, in particular over the past 60 million years. Now, mountains erode very quickly, and there's naturally a small amount of acidity in the atmosphere. In fact, we'll talk about this more later on when we talk about the erosion of landforms. This is in the form of carbonic acid, and it forms when carbon dioxide in the atmosphere combines with water vapor. So the rain that falls out generally is slightly acidic, about a pH of about 5.5. Well, this carbonic acid reacts with rock, dissolves it away, and then ions like bicarbonate ions get washed down rivers and into the sea. More mountains, more exposed rock, more erosion, more removal of carbon from the atmosphere. And that carbon washes down, gets eaten by all the life along the way, plankton, which get eaten by larger things, which end up as the clamshells. Clamshells, after all, are made of calcium carbonate. So that's where that carbon goes. That organic material sinks to the bottom of the seafloor, gets locked away as limestone within the earth. And as a result, the mountains are kind of like sponges that soak up carbon dioxide from the atmosphere. The more mountains you have, the more rapidly you pull carbon dioxide from the atmosphere. Well, why is this important? Well, the carbon dioxide is a critical greenhouse gas that keeps our planet warm. In fact, the time just before the Himalayas, the carbon dioxide levels were about 4 to 8 times what they are now. And as soon as the Himalayas started coming up, the whole world began cooling. In fact, on a very long time scale, our global temperatures have been continuously cooling over the past 65 million years. And a large part of this is due to the rise of the Himalayas. So our current pattern of severe ice ages, that's also partly India's fault. As it goes up, it gets cold. Well, an interesting thing happens to air when it gets cold. It can no longer hold as much water vapor inside. So the water vapor that's from the Indian Ocean, as the air cools and goes up over this barrier of the Himalayas, begins to precipitate. It condenses first out as small ice and water droplets to make clouds, and then continues to condense to form ice, snow, and rain that falls out. As a result, there's an enormous amount of water that falls along the southern end of the Tibetan Plateau, but very little that actually makes it up on to the top of the plateau itself. By the time you get as far north as the Gobi Desert, we understand why this region is so dry now. The air has totally lost its moisture, and there's nothing left to fall there. The Himalayan mountains and the whole plateau, in fact, create a huge barrier for air masses. It also prevents cold Arctic winter winds from coming down into India, keeping India at a very temperate climate around the year. Now, there is liquid water on the plateau, and some of it in very spectacular lakes. Qinghai Lake, also known as Tso Nangpo in Tibetan, is the largest lake in China. The name means the blue sea. That's how large it is. There are numerous lakes that are considered holy to the Tibetan people there, such as Yamdrak Lake or Yilhin La Lake and Mapam Yomtso. Namso is one of the most popular lakes for tourism. It's located just 3.5 hours north of Lhasa, the capital of Tibet. The lakes here are just beautiful to visit, clear, pristine, undisturbed, surrounded by incredibly tall mountains. I mean, there's usually not beach weather conditions here, but it's definitely spectacular to view. There are many places on the plateau that can be very dry. In the Changthan region, up in the northwest, temperatures also drop to about -40 Fahrenheit in winter. So it is very dry, very cold. And in fact, it's so inhospitable, it has the lowest population density anywhere on the earth that isn't Antarctica or Greenland. Life has evolved on the Tibetan Plateau in totally unique ways in order to adapt to the extreme cold there. It had long puzzled biologists just how rapidly and efficiently very large hairy mammals had evolved during the recent ice ages, creatures like the woolly mammoths and woolly rhinoceroses. Well, it turns out they didn't. They had already been eking out an existence up at the top of the Tibetan Plateau. But when global climates turned cold, they came down out of the plateau, finding that they were very well suited for much of the northern hemisphere. It's a theme of this course, repeated over and over, that the powerful forces of erosion are constantly ripping down the land and washing it to the sea. Mountains get eroded faster than anything else. I mean, the Appalachians, again, were once the Himalayas of their day, but after hundreds of millions of years, frankly, there's not much left. So how is it that the Himalayas are so tall? Well, the simple answer is they're just very young. In fact, they are still going up. They are our best current example of the collision between two continents. You can see this very well if you look at the animation of plate motions that I showed earlier in the course. For example, if you go to a time 200 million years ago, this is when Pangaea still existed as a large supercontinent, you can see that India was nowhere near Asia. In fact, it was landlocked in between Africa, Australia, and Antarctica as part of this giant C-shaped landmass we call Pangaea. If you start to move the clock forward, though, you can see that when the continents broke up, India moved incredibly quickly across into Asia, moving across and closing up the Tethys Sea. By 100 million years ago, it had broken away from Africa with Madagascar, but soon after, it broke away from Madagascar northward and moved towards Asia. By 60 million years ago, it had already started to collide with Asia, and as it continued to move northward, everything that lay in between India and China got smashed up to create this massive plateau that's actually still growing in the current day. What happens in that process is anything that got stuck in between, whether it's ocean seafloor, marine sediments, the existence of volcanic island arcs in the ocean there, even small microcontinents, everything became sort of collateral damage in this collision and got plastered on in between India and China. Eventually, it's no longer possible for the rock to keep going up. I mean, as the collision occurs, the rock has to go somewhere, and the rock gets forced up. At some point, the bottom part of India actually began to slide beneath China. And now we have a situation beneath the southern part of the plateau where you have, well, for the top five, let me start first with the Andes in South America. As I already mentioned, the Andes are the longest mountain range in the world. They also have another tall, vast plateau, the Altiplano, which is formed both by tectonic processes and volcanic processes. It's high in elevation. It tends to be very dry. And we'll talk about this more in lecture 30. Now, the Andes change their appearances as you head from the equator down towards Patagonia. They become increasingly snow-covered and therefore eroded by glaciers as you move south into the southern hemisphere. The Andes began to form a long time ago, at least 1 billion years ago, from multiple plate collisions, some of which we're not even sure what they were. Several of these were continent-continent collisions, like the one that's currently forming the Himalayas. It's often the case that supercontinents like Pangaea will open and close along the same borders. So the same mountain range might have multiple episodes of growth, and that has happened with the Andes. The Andes have also grown continuously over the past few 100 million years with a nearly continuous subduction zone there. So the big Nazca Plate, part of the Pacific Ocean seafloor, has been sinking down here for a very long time, folding, deforming layers of sedimentary rock, taking big wedges of accretionary sediments, the stuff on the seafloor that gets scraped off as these subducting ocean plates sink down back into the mantle. This sediment gets added on as well. And of course, you have volcanoes there as well, adding more rock to the mountains. Next, we go to Alaska for Mount McKinley. I already mentioned that Mount McKinley is the single largest mountain. Simply in terms of its total mass, it dwarfs Everest in comparison when you put it side by side. Everest has the advantage that it's already starting out on top of a huge Tibetan plateau. Mount McKinley is part of its own long mountain range, the Alaska Mountain Range, which goes for about 1,000 kilometers. Next, let's go to the Rocky Mountains in North America. We saw this 2 lectures ago in the Burgess Shale, and the Rockies extend a great distance, both in the United States and up into Canada. It's about 3,000 kilometers long, begins in New Mexico, and ends up in British Columbia. In the United States, the Rockies formed 80 to 35 million years ago. It's a mountain building event we call the Laramide orogeny. Orogeny means a mountain building. And as I mentioned before, this is largely due to North America going over the ancient Farallon Pacific Ocean seafloor, and that young, buoyant slab pushed up North America and forced up the Rocky Mountains. It actually has a very complex geology. The mountain building of the Rockies happened in fits and starts over various periods. Last, let's go to Europe for the Alps, which are the major mountain range of Europe. And actually, I should say that all of those mountains, the Alps, are directly related to the Himalayas in a way. They are all part of a long mountain chain that's all associated with the close-up of that ancient Tethys Sea that followed the breakup of Pangaea that started 200 million years ago. This includes the Alps. As you go into Eastern Europe, the Carpathians and the Caucasus and the Zagros and the Hindu Kush and Pamir and Karakoram and Himalayas. If you look at a map of the topography of Eurasia, you'll see this long ridge that connects all of these all the way across. The tallest peak in the Alps is on the border of Italy and France. It's Mont Blanc. That's 4.8 kilometers above sea level. Though perhaps the best known geologic feature of the Alps is the Matterhorn, which is along the border of Italy and Switzerland. It comes to a very sharp peak that has been eroded by glaciers carving away all sides of it, leaving a stunning point, and it's a very striking landmark. Well, in this lecture, we've seen some of the geologic wonders of the giant Tibetan Plateau. In the next lecture, we're going to see what happens to all of that rock when it gets eroded away and we're going to visit the Ganges River Delta.
Okay, this is to discuss. Listen here. So, tomorrow, guys.
再见，老师。